which means we're going to take a hydrocarbon and we're going to set it on fire, okay? And we're actually not going to do that part. We're just going to get the data and use it for something, but that would be cool, but you're not going to do it. Okay, so when we do this, we're going to assume that the law of conservation of matter works, and that's going to provide us with everything we need. We're going to get the mass of the CO2 and get rid of the moles of carbon, and we're going to mass of the water to get rid of the moles of hydrogen. We'll do the same thing for nitrogen if it's present. And the oxygen's the tricky part, because when you react something with H2O, right, the H2O is kind of uncontrolled. So what we're going to have to do is compare the oxygen that we had on the reactant side, right, to the oxygen we're going to have on the product side. If this number is bigger, that means some of the oxygen that's in the products had to come from the actual original compound. That would mean there's oxygen in the hydrocarbon, which is possible, right? And that's what we'll do, figure that part out. Okay, so let's start, right? The easiest way I can do it is write out the equation. HC plus O2 yields H2O plus CO2. Now I wrote it like that, HC, because I'm not sure what they are. I could also put X and Y next to it if I want to. And I might have oxygen in here, I'm not sure yet. Okay, so then we'll go ahead and set it up. So CnCO2, we'll start with 23.118 grams of CO2 times, we'll convert it to mole, because mole is a nice transferable quantity, like that. And then we'll go ahead and get rid of those, convert it into moles of carbon. So 1 mole of CO2, 1 mole of carbon. So there, right? And then I end up with, let's see, 23.118 divided by 44, which gives me 0.525 mole carbon. Okay? And we'll do the same thing for water and H2O. We'll use the numbers we have, 4.729 grams of H2O, and we'll convert it into moles. 1 mole H2O is equal to 18 grams. Those cancel. And then we'll convert it into moles of hydrogen. And we know for every 1 mole of water we have 2 moles of hydrogen, H2O, right? And we'll do our math, and we end up with 0.525 mole. What do you know? Same one. That's good. Right? And now we'll do the oxygen in the O2, right? So what we'll do is take the 18.214 grams of O2 and we'll convert it into moles. 1 mole of O2, 32 grams, times 1 mole of O2, 2 moles of O. Okay, so then we end up with 18.214 times 2 equals, divided by 32, which is equal to 1.14 mole of O. Okay, but we have to be able to compare the mole of O2 in the the moles of O and O2 to the mole in the product. So the mole of O2 in product is based on the relationship between the carbon and O inside the problem here, and then the O and the H in the water. What we're going to do is for every 1 mole of carbon I should have 2 moles of oxygen. So that's the moles of carbon. So 0.525 times 2 gives me 1.05. And for every 1 mole of hydrogen I should have just 1 mole of oxygen because it's H2O. So I have to divide that one by 2. So we end up with 0.2625 mole. I'll add them up, 1.3125 mole. So on the product side, I have 1.3125 mole, but on the reactant side, I have 1.14 mole coming from here. That must mean there's some oxygen that I just haven't solved for yet. And I think I can do it by subtracting these two. The difference between them should tell me how much oxygen is present here because of the law of conservation of matter. Oxygen on this side should be equal to the oxygen on this side. So we'll subtract them, 1.3125 minus 1.14, and it will give us 0.1725 roughly of O. And that's O in the compound. Now, empirical formulas work like this. Okay, you're going to go ahead and take the one that's in the smallest number, the number of moles in the smallest amount, which would be this, this, and this, and divide each one by the smallest one. So for example, 0.525 mole divided by 0.1725 is going to give us 3. And I don't have to do it twice because it's the same one. And then I know what, if I divide this number by itself, I get 1. So empirical formula is going to be C3H3 no. Okay? We'll do the next one. This probably should be number 1. It's probably the easiest one of the bunch. I will do this out the same way. CXHY, plus O2 yields CO2 plus H2O. And we have excess oxygen. Let's see. Oh, that sounds weird, right? We have excess oxygen. Petroleum compound has 38.196 grams, right? And 18.752 grams of those two. We have excess oxygen. Okay. So that's going to be a little bit confusing for me, but that's all right. All right. So let's do the C in CO2. And so we have 38.196 grams times the molar mass CO2, which is 44 grams. And for every 1 mole of CO2, we have 1 mole of carbon. So we end up with 38.196 divided by 44, so 0.868 mole of carbon. And then we'll do the HNH2O of 18.752 grams times 1 mole of H2O, 18 grams, times 1 mole H2O has 2 moles of H in it. Okay, cancels out. We end up with 18.752 times 2 divided by 18. 2.08 moles of H. Okay, we got those two. Now we're going to figure out the number of moles of O. Okay. So, let's see. This is 12.501 grams. All right. Oh, it doesn't contain oxygen, which is nice. It makes it easier. All right, so we got everything we need, right? Establish the empirical form of the compound. Well, those are my two numbers. I don't have any oxygen inside this, so I'm going to divide by the smallest one in both cases, just like you would do for any empirical formula. Right, and you end up with 1, and then 2.08 divided by 0.868 equals 2.4. Okay, so the ratio is 1 of these for every 2.4 of these. And since I needed empirical form of the whole number ratio, I got to figure out what number I'm multiplying by here to get to that number. And I think I multiply each of these by 5. And it was C5H12. Because it's 1 to 2.4, which should be the same as 12 to 5. Okay. Keep moving. All right. In the course of combustion analysis of an unknown compound, 12.93, so on, take a minute, read. There's nitrogen in this one, which is going to make it kind of not attractive. All right, so we end up with CHXYO, and then we'll go N, I don't know, we'll call it W, right? Okay. You're going to burn it. You need oxygen. CO2, H2O. You have, let's see, 11.014 grams of this, 10.573 grams of this, and that's how much you need, right? Not any excess. And we have nitrogen left over on this side, so 2.057 grams, 12.923 grams. Where's the water? There's 6.608 grams. Okay, so we're going to do the same way we did before. We will do C in CO2, H in H2O, N in N2. It seems like that one should be a little bit easier. And we'll do the exact same thing each time. 12.923 grams times 1 mole CO2, 44 grams, times 1 mole of carbon for every 1 mole of CO2. And this one, 6.608, grams of H2O times 1 mole H2O, 18 grams, times 2 moles of H for every 1 mole of H2O. Those cancel, right? And cancels and cancels and cancels and cancels. And then the end, 2.057 grams of N, 2 times 1 mole of N2, 28 grams, times 1 mole of N2 for every 2 moles of N. And we end up with these all canceling out nice and neat. So it's the first one, 12.93 divided by 44 equal to 0.294. And 6.608 times 2 divided by 18 equals 0.734. And then we have 2.057 times 2 divided by 28 equals 0.147. Okay? We have all those. We'll figure how much oxygen we have, right? O present. So we would make this one double because there's 2 O's in CO2. So 0.294 times 2 equals 0.588. And we half this one because there's 2 that way. So 0.734 divided by 2, 0.367. Okay? And we don't worry about that one at all because, well, 0.147 is just N2, right? So we'll add those 2 up. 0.588, 0.955 mole. Okay? Now, let's do the O on the reactant side so we can see it. And we have 10.573 grams times 1 mole of O2 for every 32 grams times 1 mole O2 for every 2 moles of O. Those cancel, right? 10.573 times 2 divided by 32 equals 0.661, essentially, right? So this is how much I have on that side. This is how much on the reactant side. So this is the reactant. That's the product. There's a difference of 0.294 moles. So this 0.294 mole extra, has to come from the compound. Right? So that means we can convert this into moles as well. So we end up with, that's the C in the compound, that's the H in the compound because they're conserved, that's the N in the compound, and that is the O in the compound. We end up with 0.294 divided by 0.294, which gives us 1, right? 0.73, sorry, that's not right. 0.294 divided by 0.147, which is 2. 0.734 divided by 0.147. 0.7, I feel like it's 6, but what the heck, what do I have? Divided by 0.147 equals, leave it again, equals 5. And then that's the same as the first one. So we end up with C being 2, H being 5, N being 1, and O being 2. That's the empirical formula for number 3. All right, got 2 more to go if I can find them. Four and 5. All right, number 4. It says a biological substance, well, let's skip down here, number 4. Burned in air, oxygen, that much carbon dioxide, that much water, that much oxygen. Determine the empirical form of the substance. CH and O reacts with O2 to produce CO2, H2O. And this is 7.749 grams. This is 18.942 grams. And let's see, it started with this much oxygen was on the reactant side, and this much was on the product side. So I feel if I subtract them, I should get what's actually used. Because right now, just tell me it's on both sides. So 50.123. In fact, the other one gives us 13.776 grams of oil. Okay, that's how much is used. All right. All right, so what do we got here? Let's see. I don't even know if this is that important, the 12.915 at this point in time. Let's see if we can figure stuff out. We're going to do it again. CnCO2, 18.942 grams times 1 mole of carbon. CO2, carbon dioxide, 44 grams. Times 1 mole of carbon dioxide for every 1 mole of carbon. Okay, so we end up with 0.431 mole. And H in H2O. So we have 7.749 grams H2O times 1 mole of H2O, 18 grams, times 1 mole of H2O for 2 mole of H. Those cancel, and so on. We end up with 0.861 mole. Okay? So then we're going to do the O used. O in products. So 13.776 grams times 1 mole O2, 32 grams O2, and then 1 mole of O2, 32 moles of O. 13.776 times 2 divided by 32 equals 0.861. Okay, now we got to figure out the amount of O in products. So we're supposed to double this one, so 0.861. We're supposed to have this one, 0.43. When we add them up, we end up with 1.29. Okay, so this is the amount of O in the products. And this is the amount of O, that was used. Okay. I mislabeled this. Okay, the difference between the two should tell us how much we pulled from here. So we end up with 1.29 moles minus 0.861 moles. We get 0.43 moles. Okay, so let's just restate it. Ready? This one shouldn't have said products used. This should be the amount of O contributed by the O2. Yeah, that's a better way to say it. Contributed by O2. And then this is the amount of O total on the product side. That's the best way to say it. Okay, so this is the amount of O in compound. Right? So then we have 0.43, 0.43, 0.861. So I think we end up with this one being divided by 0.431, this one divided by 0.4381, and that one divided by 0.343. So we end up with C, H is 2 over min O. Okay, number 5, and we do it the same way, right? CH plus O2 yields CO2 plus H2O. Now I can go ahead and put it above like this, which I probably should for every one of them. I'm not sure if I did it for all of them, and we have 33.658 grams of oxygen. Okay? All right, so here we go. We got to get the lowest number ratio of the hydrocarbon, and it could have oxygen inside of it. So we'll do the same thing, C in CO2, H in H2O, and O in O2. Okay, and we have 33.057 grams of CO2. We have 10.816 grams of H2O, and we have 33.658 grams of O2. Okay, we'll convert them into moles. 1 mole of CO2, 44 grams. 1 mole H2O, 18 grams. Okay, and then 1 mole of O2 is 32 grams. Those numbers come straight off the periodic table. And then for every 1 mole of CO2 I have 1 mole of carbon. For every 1 mole of H2O, I have 2 moles of hydrogen. And for every 1 mole of O2, I have 2 moles of O. Okay? We'll cancel. Look at all this canceling, right? And we end up with, let's see, 0.75 mole, 0.751 mole of carbon. Do all our canceling in here, right? We end up with 1.202 moles of H, right? And let's see, 2.10 moles of O, right? So then I got to figure out the O in the product. How much do I have? If it matches this one, well, that means there's no O in the compound, but it hasn't so far. So let's see, ready? So we'll go ahead and it's a 2-to-1 ratio between O and CO2 and C, right? And CO2. So if I have 0.751 times 2, then I end up with 1.502 moles of O. And then I have 1.202 moles of H, but it's a 1-to-2 ratio here as well, but it's the opposite way. 1.202 divided by 2, which gives me 0.601. And then when I add those up, I get about 2.10, which tells me these are the same. Which means I only have to worry about the C and the H. And the ratio right now is 0.751 to 1.212. So if we do this, then we get 1. Do this, do this one in the calculator, we get a weird number. Let's try it again. 1.202 divided by 0.751, which gives me 1.6. The ratio is 1 to 1.6. Okay? And it can't be that way. It's got to be a whole number. So I got to multiply by some number to get this thing to go ahead. I think if I multiply by 5, I end up with C5H8. Okay? I think this is the one. So we multiply, by, well, I can't spell it all. Let's try that again. Multiply by 5. Whole number ratio. And that is number 5.